So the title, as I mentioned before, is Using Robots for Milling. The different topics we're going to be covering is starting with the setup and preparation of a part for CAM programming using MecSoft CAM products. So we're going to show that piece in the MecSoft CAM products. We're going to be showing 3 to 5 axis programming, 3 to 5 axis toolpaths, and also the post-processing, how we actually take it down that path where you start the toolpath programming and then doing the post-processing. And then we hand it off to the RoboDK product where you can define the robots and work cells. And then also we'll show the process of how we transfer the CAD model as well as the posted code from the MecSoft CAM products to the RoboDK product. And then finally, we'll be showing the verification of the robot motions in RoboDK and then sending the robot language or the robot code from RoboDK to the robot controller. So these are the topics we'll be covering. And so without any further delay, I'll have Uday take over the demo.
Thank you, Joe. Hello, everyone, and thank you for joining us today for this webinar on using robots for milling. Today, we will be giving you a demonstration of our RhinoCAM product, and the same can also be accomplished in any of our MecSoft CAM products, which could be Visual CAD CAM, Visual CAM for SolidWorks, and a LibreCAM as well. So what I have currently showing on my screen is RhinoCAM. RhinoCAM is a plugin for Rhinoceros, runs in Rhinoceros 6, which is 64-bit, as well as Rhino 5 64-bit platforms. As you bring up Rhino with RhinoCAM installed, you will notice that the RhinoCAM menu appears right across the top of your screen, and RhinoCAM offers several different modules. We have milling solutions for 2 to 5 axis CNC milling and routing applications, 2-axis turning solutions for CNC lathes or turning centers, a brand new module for programming mill turn solutions. Profile nesting and G-code editor also are 2 brand new modules that are introduced in our latest version, where you can nest profile toolpaths that you generated in MecSoft CAM products. G-code editor module allows you to verify your posted G-code generated from MecSoft CAM products, where you can run G-code simulation as well as backplot. Mesh module offers you mesh editing, mesh healing, mesh repairing, mesh fixing, which can be used for CNC milling applications or could also be even used for 3D printing application, where you can also generate supports and export the mesh either as STL or G-code. We also offer parts nesting, where you can nest parts into a sheet, and also art, where you can take convert art to part, which could be 3D reliefs, or you could do raster to vector conversions. Now, today's focus will be primarily on our milling module, where we're going to talk about how we can program milling operations for 2 to 5 axis applications. RhinoCAM's mill module is offered in several different levels or configurations, starting with Express, Standard, Expert, Professional, and Premium. So depending on your machining needs, we can help you determine what configuration works best for you. You can also find information on each of these configurations on the feature list on our product page. Now, as we select RhinoCAM and Mill, you will notice the RhinoCAM's interface, which is the machining browser, appears docked over here on the left half of your screen in Rhino. There's 2 main tabs in the machining browser. You have the Program tab and the Simulate tab. The workflow is typically working our way from left to right as we work through these groups under the ribbon interface in the Program tab. Once you have your toolpaths generated, you can switch over to the Simulate tab to run the cut material simulation. Now, the Machining Objects browser, which can be docked below the machining browser or could be docked over to the side, allows you to create tools, or you can bring in your library of tools that you've already defined, and allows you to create different types of tools: ball and mills, flatten mills, corner radius, tools for engraving, chamfer, taper, thread mills, face mills. You can also create form tools, dovetails, fillet mills, lollipop cutters, form tools or user-defined tools, as well as several different drill types: drill, center drill, reamer, tap, bore, reverse bore tools. Tools can be defined under each of these tool types, where you can specify the parameters for the tool, you can preview the tool, set your tool numbers, and also you can establish feeds and speeds where you can enter in the feeds and speeds or use the built-in feeds and speeds calculator in here to establish feeds and speeds based on the tool and the stock material. Now, each of these parameters that you define can then be saved and saved to a tool library. Now, today we'll talk about how we can program this part that you're seeing on the screen here using a 3-axis operation. By looking at the part, you can see there's sculpted surfaces on the model. So parts like these would typically require all 3 linear axes, X, Y, Z axes, to be able to machine and program these toolpaths. So the first step is we want to go into the Program tab and select Machine to define the machine definition. So we set the number of axes in here. So for 2 and 3 axis applications, we would leave it as 3 axis. You could also pick 4 and 5 axis depending on the type of parts you're trying to machine. So once you define the machine tool, the next step is to select the post processor. RhinoCAM includes post for over 300 plus different controllers in here, and this covers a wide range of machine tools that are out there. Now for our application today for robotic milling, we're going to be selecting AppCLS IJK, which could be the post processor, or it could be outputting in a G-code flavor, which could be like a standard FANUC output. So for our today's demonstration, I'm going to use AppCLS IJK and set the output file extension to .apt for apt. So as we define these parameters, you'll notice that the machining job, the information and the machining job automatically gets updated in the tree. The next step is to define our stock, which would be the blank of material, the workpiece we're going to be starting with. There are several different ways how we can define stock. For this particular project, I'm going to use box stock. And the system automatically determines the minimum extents of the stock required based on the part that you've designed. So I'm going to change my stock height to 4.5 inches and pick OK. So you could be programming either in inches or metric, which is millimeter units with RhinoCAM. Once you define the stock, we can display the visibility of the stock. The stock now appears on top of the part. You would then align the stock to the part. In this process, I'm going to align the bottom of the stock to be flushed with the bottom of the part. The next step is to establish our origin, which could be called the work 0 or the program origin or the part coordinate origin. We can do this by using align set world coordinate system. I'm going to choose set to stock, pick the lowest Z and the center in X and Y. So you'll notice that your XYZ origin is now set to the bottom of the stock and center in X and Y. Once this information has been established, you're now ready to machine this part. You could also pick the material that you're going to be working with. It could be wood, it could be working with metal, depending on the type of material. For our application today, we'll just pick wood, pick OK, and we can also display the texture of the material during simulations. I can apply a material texture as well. So switching back to the Program tab, we're going to start programming this part using a combination of 3-axis operations. RhinoCAM offers you a wide range of toolpath methods, starting with 2-axis milling, or also known as 2.5-axis milling. You have facing, pocketing, profiling, V-carve, roughing, finishing, engraving, slot machining, chamfering, filleting, hole pocketing, hole profiling, thread milling, T-slot machining, and remachining. Now in the 3-axis, we offer a wide range of 3D methods, starting with roughing, re-roughing, several different types of finishing techniques like constant 3D step over pocketing, pencil tracing, remachining, steeps machining, radial spiral machining, curve between curve machining as well. RhinoCAM's 2 and 3-axis methods also offer high-speed pocketing toolpath methods, which can be used in 2-axis pocketing, slot machining, as well as 3-axis roughing operations. RhinoCAM also includes 4-axis methods for programming both indexed as well as continuous 4-axis and simultaneous 5-axis, in addition to indexed 5-axis as well. So we will be covering several of these methods during our webinar today. So the first process is to start with the roughing process. We're going to use 3-axis and roughing. In this particular step, I'm going to select a tool for roughing. So we'll use a 3/4 inch end mill. The feeds and speeds, as you can see, they're automatically loaded from the tool. Clearance plane refers to the safety plane for your transfer motions and the non-cutting motions, and the plane is automatically displayed when you're in the clearance plane tab. Specify your cutting parameters, where you can choose your tolerances, your cut patterns. You can choose your step overs in here, as well as you can establish your cut levels, engage in retrack parameters, any advanced cut parameters, and then selecting generate will automatically compute your roughing toolpath based on the part that you modeled and the stock that's been defined. So we have our roughing toolpath in here. So this is roughing in levels. As you can see the roughing toolpath, I'm stepping through each of the levels. So once we are through with the roughing operation, I'm going to switch over to the Simulate tab and click on Play to run our cut material simulation. You can control the simulation speed in here to have it go faster or slower as you wish. So there's your cut material simulation for the roughing process. In the next step, we're going to go ahead and program a finishing operation. This could be a finishing or a pre-finishing operation. I'm going to start out with a parallel finishing operation. We'll select a tool. Typically, you would want to use like a radius tool. It could be a ball mill or a corner radius tool. The same process would apply for establishing feeds and speeds and clearance. Establish your cutting parameters. You can choose your cut direction, angle of cut, your step over control, and then generate. Create your toolpath. Now, as you notice here, I did not have to select any surfaces or boundaries. The system will automatically compute the toolpath based off the part that's visible in here. So there's our 3-axis parallel finishing toolpath. And again, we can switch to the Simulate tab and select Play to run the simulation. And if you'd like to run through the simulation here, you could always select Pause and then pick Simulate to end to skip through the simulation. Now to go back and machine certain areas, finish certain areas on the part, let's say we would like to go back and refinish these areas, I could make a copy of the existing operation, right-click copy, right-click paste, or you could use Control-C, Control-V to copy paste. And now I'm going to use selection of part surfaces, so I can individually select the surfaces I would like to use for machining here. So I'm quickly picking a bunch of these surfaces, right-click, specify my cutting conditions in here, and then generate. So we now have a finishing toolpath that is just limited to these surfaces, and I chose the surface extend condition to go past it, so it does a nice overlap with the previous operation. Now let's go back and clean up these areas where you see these bitangencies to clean up all of the scallops that are being left in here using a 3-axis pencil tracing operation. We'll use the same tool and then generate. So let's run a quick simulation of the last 2 operations in here. And now we are ready to post-process these operations, which can then be programmed using RoboDK. So I'm going to post-process these. Now, before I do that, I can take a look at an estimated time to establish how long it would take to mill this part. So it estimates based on the feeds and speeds that you put in to program the parts in addition to your cutting parameters. Once you have these programmed, you could also go ahead and do a post-process. Before that, I also want to show you how we can generate what's called a shop documentation, which would be like a setup information sheet that would allow the operator in the shop floor to learn more about what the tools being used in the program, what are the stock dimensions, and what are the various parameters that are in here. So the shop documentation allows you to generate these in here. So once these are generated, we would be able to go ahead and do a post-process, and the post-process will generate the G-code output file in here. So right now, I am outputting the shop documentation in here. So this is going to be output in like we can output it to either to an Excel, as you can see right here, or it could be output into an HTML format. It's the choice is yours. Now let's go ahead and post-process the code. So I'm going to select the setup, or I could pick the machining job, right-click and do a post all. The posted code is now ready to be output. I'm going to click post, and the posted output file automatically appears in a notepad or the text editor that you pick. Now, once you have the output posted, you can output the model to RoboDK. Once you have the RoboDK application installed and the RoboDK tab appears in Rhino, you can choose load part. Now, to give you a demonstration and talk more about RoboDK, I'm going to request our special guest Albert to present this to you.
Okay, let me share my screen. All right. So once you have the project ready in RhinoCAM, first make sure that you are choosing the right post processor. A post processor should be the APT-CLS-IJK, and you have to send the program to this RoboDK batch file. So once you install RoboDK, by default, you'll have RoboDK installed on the C drive. RoboDK, you have to go to Other. Then you have to select Plugin MecSoft. And then this is the batch file that will automatically send the posted file to RoboDK. And also make sure to select the extension APT. Other posts may work as well, but this is the one we're using internally to test everything and make sure everything works correctly. So you can right-click your project, select Post All. Make sure to choose a meaningful name. So it will be the same name that will be used in the controller when you generate the program for your robot controller. And here we can see that the 4 operations we had in RhinoCAM, they're visible here, and they've been automatically split by tools and operation. There are some settings here that have been automatically preset by the plugin. There's a default setup with a KUKA robot, a default spindle with a tool holder, and the 2 tools have been added and pre-selected here. So this is the same menu we could reach by selecting Utilities, Robot Machining Project, and we could provide the file of our machining program. So everything has been selected automatically. You can optionally add some approach and retract settings. These will be added to your existing approach retract you've defined in your in RhinoCAM. So right now, without going into more details about this menu, using the default settings, so basically this menu will help you convert any 3 or 5 axis task for a CNC into a robot program. So if you select Update and Simulate, this will be the default settings. They already generate a valid simulation. Haven't changed anything here yet. So if you select all the other machining operations, right-click and update programs, everything will be updated accordingly. As it calculates, it will generate 1 new program linked to each machining program. So this is basically the toolpath, 5-axis toolpath, and this is your 6-axis robot program. The main program has also been added automatically, and it will call the sub-programs in order, so you can quickly simulate. And already we can have a valid program using default settings. You could select all the programs that we have here, generate robot programs, and we would obtain a robot program. So this is a program we could send to the robot. This is the main program. It calls a sub-program, so each file will be a sub-program. And in this case, we're using KUKA robot, so it's an SRC file. We can see that the base is defined here, the tool is defined here. We can also see there are some additional calls that are part of a custom integration you could do to change the tool according to an ID and run your spindle based on your RPMs. These actually can be controlled from program events. So in program events, you can customize if you want to trigger this from your from here or from inside the program you generate, or if you're gonna trigger your programs from somewhere else, then you may manage this automatically, so you could just delete that. Once you have, so to go more here into detail, so basically this will help you define the additional degree of freedom you have with a 6-axis robot. So basically, right now, a machining operation has a certain orientation for the tool. You may want to change this orientation and let's say do the machining operation using this orientation. So right now I'm using the Alt key to change, to move the robot and change the orientation. You could adjust, align the orientation of the tool by right-clicking the robot and say Align Tool Orientation. And by selecting the Teach button, you're telling this menu that holds the settings for the first toolpath to do the machining operation in this manner. As you select Update and Simulate, now you can see that the machining operation is updated with your preferred orientation. This setting you see here, it's optimization parameters. This will automatically rotate around the Z-axis of the robot if required to make the path reachable. So if you have a very large part, or you have your part is working, you're working really far, you try to select Update, you'll see a red check mark. That means that your program is not feasible. As you bring your part in the workspace, you will see that the orientation starts to change. That's because the robot has no choice but to change the orientation around this 6 degrees of freedom to make the path reachable. So if you were to block right now, that the orientation was changed automatically, of course, this means we're working near singularity on axis limit. So if you were to block this and set to 0 and try to update this, there's no way robot can do that. So in this case, since we're using a very simple project, you can bring the part in, keep that to 0, select Update. This will be calculated much faster. And as you select Simulate, the result will be the same. So having changed that, you could also change the start point here, which will define a different robot configuration for your starting point. But once you have settings defined for your first machining project, you can right-click, select Copy Settings. You can bulk select the other machining operations and select Paste, Update. And this will recalculate the programs, and you can see now the calculation happens much faster. And if you double-click a main program and run it, it runs as we wanted it. And again, you could just right-click and generate robot program. This will generate the updated program. So right now, by default, if you use a KUKA robot, we're using a KUKA KRC2 post processor. You can customize that by, if you have a KRC4 controller, you could change that here. We have other post processors. Depending on the robot you use, you'll have a post pre-selected. These post processors, they all come with a default install, and you have access to all of them. You could right-click the robot, select post processor from here, or right-click a program, select post processor, any setting, once you change the post processor, it applies to the whole project. Once you're done with the project, you could select file, save as, and you could save it as an RDK project. And these would hold information about the whole cell, the robot, the tools, coordinate systems, and your machining programs. So I think, oh yeah, and I forgot to mention that I didn't load the part, but you could install the Rhino plugin. We have a documentation online, so you could select load part. This will load the part automatically to your active reference frame. So if you were to hide this, you would just see the part. It's the same part that we exported from Rhino. And there's more help. If you select F1, this will take you online, and you'll have you'll have access to our online documentation to go more into details. So that's all I wanted to share for this example. Maybe we can move to the next example, Uday.
Thank you, Albert. So folks, just to give you a quick application workflow overview. So the CAD is where you would be designing or importing your files into. So it could be designed in either in your CAD system or Rhino or SolidWorks or whatever CAD system is that you're using of your choice. And once you design the part, you would then program and generate toolpaths using MecSoft CAM application, which could be RhinoCAM or our standalone Visual CAD CAM or Visual CAM for SolidWorks or even a LibreCAM. So once you generate the toolpaths in MecSoft CAM product, you would then transfer the posted output file into RoboDK to be able to program the robotic arm or the robot station. And the output that you generate from the robot will then be transferred into the robot controller to actually physically run the machine tool. So this is just a quick workflow. I forgot to show this at the start of my presentation, so I apologize for that. So now let's jump into the next example where we'll talk about how we can do 5-axis programming, and then which you can then take it into either a 6 or a 7-axis robot. So what I have here is a prototype model of a car, which requires programming using multi-axis. It can't just be done with a 3-axis setup, so we will have to program it from different orientations. So parts like these can also be programmed in RhinoCAM by taking advantage of our 5-axis toolpath methods. So RhinoCAM offers several different types of 5-axis continuous or simultaneous methods, starting with curve machining, flow curve machining, between two curves machining, drive curve machining, surface normal machining, and swarf machining. So there are several different types of 5-axis methods that are offered in RhinoCAM. And typically to program a part like this, you would still go through the process of roughing it out. For roughing, we would recommend using indexed or also known as 3+2 machinings, where we rough it from different orientations or different planes. I'm going to cover that in my next example. On this particular part, we'll talk about how we can generate some 5-axis simultaneous finishing toolpaths. Now, the 5-axis methods requires you to select surfaces for machining, and you can also pick curves or drive curves for machining. So to determine how you want the toolpath to be generated. So in this particular example, I've selected these two surfaces as my drive surfaces, and as you pick these surfaces, the surface normals are automatically being displayed, and if you need to reverse or flip the normals, you can use these controls in here to flip the normal direction. So you want to make sure the normal directions are pointing correctly from the direction you want it to be milling the part. And these drive curves can be selected either by selecting a surface edge, or you can pick a curve that you already have modeled in Rhino. You would then basically go through the process of selecting the tool, establishing your feeds and speeds, and you can set the clearance. So in 5-axis, the clearance can be set to either a planar, it could be spherical, or it could be cylinder. So depending on the type of part you're working on, you can specify the clearance type. And of course, you have the control to control your cut parameters, your cut traversal, tool axis control. And finally, in 5-axis, you would also want to make sure you specify a gouge check. You want to make sure that you don't collide or gouge into any adjacent surfaces. So these can be set right here. Once you generate the toolpaths, you can see the toolpaths are displayed, and also you can see the normals are being displayed for the toolpaths as well in here. So this method is called 5-axis between two curve machining, and I'm going to run an animation of this toolpath in here rather than doing a cut material simulation. So I'm going to select play, and you can see the tool remains normal to the surface being machined, and the normals are derived based off the surface that you selected as your drive surfaces. So folks, if you have any questions, you're more than welcome to post those questions in the questions panel at this point of time. Thank you. So we've just machined these two surfaces. The next step I'm going to do is machine the surfaces on the hood here using the same technique between two curve machining. And I have these two surfaces selected. And we generate the toolpath similar to what we did for the previous surfaces. And since I've chosen these as the gouge check surface, it automatically checks against these surfaces for gouges or collisions, and you can either retract along those surfaces, or you can say leave out the gouging points, depending on how you want to handle the gouge checks. So as you can see, the tool stays normal to the surface being machined. Now in the next example, what I'm going to show here is how we can use the side of the cutter to remain parallel to the surface. So this can be done using a technique called swarf machining, and where you specify or select your wall surfaces in here. So in this particular case, we are selecting these surfaces as our wall surfaces, and then we can either pick a floor curve or we can pick a floor surface, and the cutter side of the cutter would remain parallel to the surface as you're machining it. So I'm going to run a quick animation of that as well. So there's our swarf machining, and I could apply the same for the surfaces over here on the window panel as well. Now we can also take a look at these coordinates and your primary and the secondary axis angles in your toolpath editor, where you can see each of these XYZ coordinates along with your primary and the secondary axis angles that are computed for each of these toolpath motions. Now, typically for a robotic arm, the 5-axis setup would be defined in the machine tool setup, where you define the number of axes as 5, and for CNC robots, you can set it to head-head configuration, your primary and the secondary axis of rotation. We also support additional configuration types for like table head and table table. If you're working with like a CNC mill that has a trunnion type of 5-axis setup, or a table head, which could be a combination of a rotary table or a head. Now for robotic milling applications, you would set the configuration as head-head. Once you have these tool paths generated, you would want to then post-process these out to your machine tool. So right-click on a machining job and select Post All. And I'm going to specify a name for the file and then select Post. Now the posted output, since we chose the post as appcls ijk, rather than outputting the primary and the secondary axis as angles, it's going to output them in ij and k, ijk vectors. So there is the posted output file, which you can then transfer it into RoboDK. You can transfer the part as well, and then machine this part on your CNC robotic arm. So to demonstrate this process, again, I'm going to go ahead and request Albert to share his screen and give you a quick overview of how this part, 5-axis part, can be programmed in RoboDK. Thank you.
I'm going to share my screen. Perfect. So once you have a project ready in RhinoCAM, you make sure you're posting the APT file to RoboDK. Right-click, Post All. Make sure you select a meaningful name, and this will load in RoboDK. And again, you'll see the same operations that you have defined in RhinoCAM. So let's say in this case, it opened the same KUKA setup we just showed before, and you could select Update here or select everything, update programs. This it works out of the box. There are no additional settings to change. We could right-click and generate program. But let's say in this case we want to use a ABB robot. You could, if you've worked on a project and you're replacing a similar sized robot, you could right-click, select Replace Robot, and you could choose an existing robot you have in your library. But for this example, I'll show you how to build a new RoboDK project from scratch. So if you select this button, will open the online library. You can also access it from File, Open Online Library. You can select filter robots by brand. Let's say we're looking for a 20-kilogram payload robot. And let's say this reach would be enough for us. You can select Download. We'll open in RoboDK. Each robot will be added with its own coordinate system, so the base of the robot. You could also load step IGES STL files. You could drag and drop them into RoboDK, it will be loaded, or you could select File, Open to load them from Explorer. You could create a new coordinate system here or here. You could place your files, 3D models, by drag and dropping it within the tree. So with a shift, you bulk select and drag and drop them in coordinate system. Here you can see the spindle. You can drag and drop to the robot. So as you drag and drop it to the robot, it will create a tool. The tool already is matching the coordinate system of a model is snapping on the robot flange. You could double click the tool, and here you could adjust the 3D geometry if needed. But what's most important is the TCP. It's the tool center point. So it has already been defined here, but you could enter the XYZ WPR values manually. You could also select ABB quaternion and enter them directly from quaternion data. If you have an ABB robot, you probably have quaternion. You could, with the Alt key, you can move objects like I was showing. The Alt Shift, you could change the TCP, so you would see the coordinates change and orientation as well. So if we go back to 60 degrees. And the same thing for the coordinate system. So let's say we have a coordinate system that is like the world coordinate system. We could set it to 0. Or we could select this button and reset. So all the objects now go to the origin of the station. And let's say we are going to add another coordinate system that's going to represent the machining reference. So I just selected F2 to rename. You can right click and select rename to rename your object. If you attach the coordinate system to the robot base or not, that's actually, it can make a difference if the robot base is not at the root of the station. So if you double click your coordinate system and you enter coordinates here, you have to make sure you're placing them with respect to the robot or another known coordinate system. So you could have multiple nested coordinate systems. With the Alt key, you could approximately place the coordinate system where you want it. You could double click the robot, make sure you have the spindle selected. The spindle represents the tool holder. The machining reference selected here, which is the one that has the green dot. And if you've properly set up your tool reference frame, you should see the same coordinates that you see in the robot controller here. And these are the joint values. So for a given joint values, you should see the same coordinates in your robot controller. And again, you can select quaternion to see quaternion if you prefer. So from once we've built a project, you could save this as an RDK file, save station as, and load it later if you need. From Rhino, you can post the project and select a same or different name. This will reload the whole project. And right now we can already try with the default settings, update everything. And we now have a working program with ABB robot. So you could already select the main program, generate. This will open actually VS Code. So it's a text editor that we provide with RoboDK. And it already has some syntax highlighting for most robot brands. You'll notice a difference of ABB. For ABB controllers, it's more common to have one module that has multiple functions. You'll find the main program automatically triggering a subprograms. And in this case, you could also, if you don't like your orientations, let's say here we're machining here from using this orientation, the last two operations. You could change the orientation maybe to work more using this orientation. You can come here, select teach, update, simulate, and copy the settings from here, paste them here, and then update. So now we should have a more reasonable setup. You could also define a move home command. So let's say you want to move the robot to a given position between steps. you could create a new program and joint move. This could be a move home. So you could rename this to go home and integrate a program call. So select escape, right click, add instruction, and program call to go home. You can copy this, paste it between each program call, double click. If you display this program, the path, you'll see that between each step, you will go to home. So it may help avoid collisions. And I didn't load the part, but you can load the part the same way I showed before. So that's everything I wanted to show for this example. I'll let Uday move to the next example.
Thank you, Albert. So last but not the least, folks, I would like to cover how we can do 3+2 machining, or also known as indexed 5-axis machining in our MecSoft CAM products. So what you are seeing here is a mesh model, or also known as a STL, or it could be OBJ. And parts, you can program mesh geometries as well in RhinoCAM or Visual CAD CAM using 2, 3, 4 axis and also index 5-axis methods. So this particular model, as you can see, there are several features, undercuts, which you can just machine from one orientation. So we would like to show you how this can be done very efficiently using index 5-axis, or also known as 3+2 machining, where you lock the coordinate system for machining to any given plane, and you can generate toolpaths. So the machine setup process is going to be very similar to what we did for the simultaneous 5-axis in here. And then to program from each orientation, we will generate roughing operations and finishing operations from each orientation. Now, by default, I'm going to use the orientation same as the world coordinate system that is typically done on a 3-axis setup. So I have a roughing operation programmed with a Z containment specified in here. In the next step, I've added additional setups where we can rotate the coordinate system for machining. It could be machining from the front, from the sides. You can use these controls on how you want them to be rotated. So I can rotate the coordinate system for machining in here. I can either select a surface, so the Z-axis of the rotated coordinate system, machining coordinate system will be normal to the surface, or you could pick a planar curve, or you could use a combination of these to orient the coordinate system for machining. So once you orient the coordinate system for machining, you'd be generating roughing or re-roughing operations, which automatically takes the stock that's being left from the previous step into account to create the roughing toolpath. So here I have generated a roughing, re-roughing operation for the front face, and then we have one for the back face of the part. So let's go ahead and run a simulation of these three in here. So I'm going to select setups 1, 2, and 3, right click and select simulate. And you could always speed up the simulation in here by selecting the checkbox to do simulate by moves. You can also toggle the display of the part while it's being simulated as well. So there's our roughing process from the 3 different orientations. And the system will automatically determine the angles on how to get from one orientation to the other. So all we're doing here is generating the toolpaths for different setups. So once we've done with the roughing operation, we could go back and repeat the same process for finishing. So all we're doing here is creating a 3-axis operation by orienting the coordinate system to different planes. So you could use any of these available 3-axis operations in here, or 2-axis operations, a combination of both 3 and 2 axis to program index 5-axis. So we have parallel finishing generated for the top, for the front, and then the back. We'll go ahead and run a simulation for these as well. Right click and simulate. And you could always speed up the simulation in here. So there's our pre-finishing, or could be a finishing operation, simulating from the front. You can see the orientation of the tool pointing towards the front, and now the tool is pointing towards the back of the part. So based on the orientation of the coordinate system that you defined, you could program from different orientation. Now, in addition to this, if the CNC robot that you're using also has a turntable, or also known as a rotary table, you can program a 4-axis parallel finishing using our 4th-axis continuous methods. And this would allow the turntable to turn as you're trying to finish this piece here. So in this particular example, I'm going to run a simulation, and you will notice that in the cut material simulation, the tool goes around the part, but on your CNC robot, the turntable is the one that rotates. So here, since we're just doing a cut material simulation, what you're noticing here is just the tool, going around the part as opposed to the part rotating. Now, once you have these programmed in different setups, you could still output all of these into one output file. So I'm going to just select a machining job, right-click on the machining job and select Post All, and this will automatically output the orientations for each and every setup. And we're outputting it to apt CLS IJK, and you can see the MSys line basically determines the orientation for each of your setups for each of those orientations in your program. Now, once you have this generated, again, the workflow would be very similar. You can load the part into RoboDK and then take the posted output file into RoboDK. So I'm going to go ahead and transfer this back to Albert again, so he could show you how effectively you can transfer this data into RoboDK and program it. Thank you.
Thanks, Uday. So once you have your project ready in RhinoCAM, in this example, I'm going to show you how you can generate a program using additional axes. So I have a setup built already. I'm not going to go into the details about showing you how to build this setup, but you can create additional axes and synchronize them with the robot. So here you can see the robot is a 6-axis robot, including linear axis for the rail and 2-axis turntable, so a total of 9 axes. You can build your own axes or import them from the library. If you build them yourself, you can select model, mechanism, or robot. You have multiple choices to choose from, including Skera or 6-axis, 7-axis robots. Once you have modeled them here, make sure the dependency in the tree reflects the dependency in the rail setup. So the KUKA robot needs to be attached to the rail. The turntable is not attached to the rail or the robot, but the part is. So once you have the dependency properly defined, you can right-click a robot, select synchronize external axis, and this will allow you to define your multiple axis system. For more information, you can select help F1, and this will take you to our online documentation where you can access, learn more about how you can build your own mechanisms or synchronize external axis. So once you have a setup ready, same thing we did before, you can post using PTCLS post processor to RoboDK. You can right-click, select post. Make sure to choose a meaningful name. So all the programs, sorry, I just opened a new RoboDK instance, so you can just close everything. You can open RoboDK again with the project that I had, and then post. Okay. So it has loaded the same operations, machining operations that we had right here. So they were loaded automatically with respect to the part reference, which is the one we had selected in the RoboDK, in the robot panel. So once we have some, you can use the default settings and try to update and see what is it that the robot can do. So let's work on the first operation only, and we can hide the other ones because we can see all the toolpaths, and it may be not easy to understand what's going on. So right now we're just doing something that looks like a 3-axis operation on the top side. We can try to simulate. So it seems the robot was able to, RoboDK found a feasible path for the robot. It doesn't mean it's optimal. So you can change and improve these settings to make something that looks more like you would like to do. So right now we can see we're working very close to the limit for joint 5. With the Alt key, you can move and say, for example, we'd like to be working more with an orientation that looks like this. So you could select Teach, and all these settings. So compared to previous setups, now we can see additional settings here to manage external access. By selecting Teach, those settings have been automatically changed to make to accommodate this preferred orientation. As we update, we're updating this program. We can double click or simulate to see what is it that it wants to do. And because we have the optimized turntable active by default, the robot is working on the same plane to let the turntable do most of the work of turning. So if we keep looking at the other machining operations, we can see that operation number 4 is very similar to 1. It's the finishing operation. To make calculations faster, you can also change this to 0 for the first operation. This will calculate the result faster. If it's feasible, it's a good sign. That means we're far from singularities. So we can just copy the settings like we did before and paste them over here. Right click, update, and we have the finishing operation for the same operation finish. So similar thing for the side operation. So we can select update and see what is it that the robot is trying to do. It may be able to do something or may not. So if it doesn't, we may need to change the settings. If it does, you may still want to change the settings to make the path feasible from, let's say, you want to be working, let's say you want to be working on the other side and with an orientation that looks like this. So you can select Teach, try to set it to 0, calculates faster. And if you can find a solution with this at 0, in general, that means you're in the good track. So simulate, and it's going to show us what is it that we're trying to do. It seems to be what we wanted. So we can right click, copy settings, and paste on the other operations that were not updated. And update. So this will generate the toolpath for the remaining operations. And with this, I'll be done. So this program is a bit long, so it takes a bit longer to calculate. So we took a look at the main program now. It will try to put together a whole project so we can see the whole milling. And actually, there's a mistake here. The tool was not properly selected, so we would have to come here, make sure we select the right tool, update, simulate. And for example, this would be the final turning operation that we were showing from RhinoCAM. So that's everything I wanted to show for this example. We covered a lot of things in a short period of time, so it would be great if you give us feedback, ask any questions, drop us a line later if you're running out of time. We'll be happy to help. I guess that we're in the questions period right now. So
Yeah.
Back to you, Joe.
Yeah, if you can switch back to the screen, Yeah, so thank you. We've come to the end. We ran a little bit over. Usually we reserve about 10 minutes for questions, but it seems there were a lot of questions we got to, and there are a few that we did not. But I think one of the things that we wanted, there were questions about pricings of the product. And as far as pricing for MecSoft CAM, it goes all the way from $700 all the way up to $10,000. So there's a whole host of configurations in between that we can customize for your needs. And then Albert, if you want to talk about pricing for RoboDK.
Yeah, so everything we've seen today is $3,500 US dollars, approximately. May depend on where you are in the world. We also have robot calibration options, which start at 15,000, but that requires dedicated measurement systems like a laser tracker or stereo cameras. We also have a network of partners that can calibrate on-site, but I would say this is the high-end, let's say, calibration needs for certain customers. Because of course we know that robots are not as accurate as a CNC, not as stiff or robust. So in general, offline programming side is enough to convert CAM programs into robot programs.
Yeah, we have a lot of customers using this combination in the packaging industry when they're cutting foam, soft material, where accuracy is not that important. So
okay,
that's something to keep in mind. Sculptures, people doing sculptures and things of that sort have them.
Right.
There was a question about pricing for universities. Yes, we do offer a special pricing for schools. The order PO has to come from universities or a school, so we'll be able to take care of that. So we do have some questions that we haven't answered. We'll definitely get to them by email, and so we'll have to wrap it up here. We're at the end. Thank you all for taking the time from your schedules and coming and attending this, what we think is pretty exciting webinar, and we're pretty excited about this partnership with RoboDK moving forward. If you have any sales or technical questions, please drop us email at either sales at MecSoft, or you can go to support as well, support@mecsoft.com, and then we will make sure to answer your questions. You can also call us if you're in North America. You can call us those numbers that's been listed. Go to our website. You can go to www.mecsoft.com or robodk.com to get additional information. So again, as I mentioned before, we will be sending out the video link of the recording of this webinar, and we'll make that available to all of you. And we will also be responding to all the questions that we haven't gotten today. Again, take care, all of you. Stay safe, and see you next month. Bye-bye.
Bye-bye.